Well, good morning. This is Larry Olson, President, Chief Engineer, and Founder of Olson Engineering and Olson Instruments, located in Wheat Ridge, Colorado. Want to welcome everyone that's attending to our presentation today on non-destructive evaluation methods for this webinar for condition assessment of masonry and stone historic buildings. I also want to introduce my co-presenter to be doing part of this, Lindsay Hazelwood. She's a certified professional geologist, senior project geologist at our Rockville, Maryland branch office. If you want to say hi, Lindsay.
Hello, everybody.
So we're going to do this.
Thanks for joining us.
Yes, thank you very much. So we're going to do this casually, meaning if you have a burning question, you can ask it verbally or put it in the chat. Lindsay will monitor when I'm speaking the first part of the presentation, and I'll monitor the chat during the last. One important note is we're happy to offer a 1-hour PDH for anybody who attends this and sends us an email to myself, and we'll get you a certificate for that for a 1-hour professional development hour. So with that, appreciate everybody that's signed in already. Seems like a decent crowd. People are still joining, so that's good. And we'll probably just keep most people muted except for the presenter. But if you do have a question, there will be time at the end to ask questions also. So we'll go through that. And with that, let's just go ahead and I'm assuming most people have now joined. It's about 2 minutes after the hour. So the very first thing we'll talk about is we do a fair amount of ultrasonic, sonic, seismic testing, and the stress waves they're called. And for those who are not as aware, a compressional or primary P wave is what we're speaking with. It's a sound wave. And there are shear waves that we also use in some of our testing. And then also in earthquake terminology called a secondary or S wave. And the surface or Rayleigh wave, the R wave, is something we'll also be talking about today, as well as some other non-destructive methods. So when you hit the surface of the concrete, or in this case, we're going to be talking about brick masonry and stone, as well as concrete masonry, that impact generates a compressional wave. That's the fastest wave, the P wave, but it's very weak. It's only 7% of the energy. The secondary or shear wave is 26% of the energy, and the surface or Rayleigh wave is 2/3 or 67% of the energy. And the fastest wave is the compressional wave, then the shear wave, and then the Rayleigh wave is 10% slower than the shear wave. And so some basic physics and elastic modulus equations are shown here. This shows the particle motion, push-pull with a compressional P wave, and the velocity being proportional to equal to Young's modulus and 1 minus Poisson's ratio divided by the so-called mass density, which is the unit weight divided by the acceleration due to gravity, times these terms involving Poisson's ratio again. The shear wave velocity is equal to shear modulus divided by rho, and the Rayleigh wave, there's a proportional relationship. Then this is given here based on Poisson's ratio. Practically speaking, in stone and concrete masonry, the Rayleigh wave is about 10% slower than the shear wave. And the shear wave is only about 61% the velocity and for a Poisson's ratio of 0.2 of the compressional wave. And the interesting thing about the Rayleigh wave is it looks like an ocean wave, except it rolls backwards with a strong vertical motion on the surface, unlike an ocean wave that rolls forward. So they call that a retrograde elliptical motion, where if shear is propagating to the right, it literally shears the particles left and right, as opposed to the compressional wave pushing and pulling them. So we use these different wave types for different purposes and different methods. So this is a more detailed slide, and I should mention that within a few days after giving the presentation, this will be posted up on our website under olsonengineering.com and resources and webinars. You'll be able to see it there if you want to view it again. But this gives those equations that were just listed, the basic velocity being distance divided by the time of travel for either a primary wave or a shear wave. The surface velocity being approximately 9/10 the velocity of the shear wave. Shear modulus being equal to the rho vs squared, where that's unit weight divided by gravity. And Young's modulus equal 2 times 1 plus the Poisson's ratio. It's really saying it's 2 times 1 plus the Poisson's ratio times the shear modulus. And the ratio between Poisson's ratio, if you measure both compressional waves and shear waves, can be calculated. These are all low strain, maximum elastic moduli. They're not working strain moduli at all. So it's low strain, highest moduli that we are measuring with these low strain tests. So interestingly enough, ACI 228.1R-89, I'm on ACI's non-destructive testing committee as well as the Bridge Evaluation Committee and Consolidation of Concrete committees. They made a rough estimate that velocity to the fourth power is proportional to Young's modulus squared, which is approximately proportional to concrete compressive strength. This kind of gets back to the working modulus equation of 57,000 times the square root of F prime C will give you a working Young's elastic modulus. So with that, you can approximately estimate the modulus and very roughly estimate concrete strength, in a sense saying it's really fast velocity, relatively strong. If it's 10% slower and you do the ratios, you will see that that comes in at about 2/3 of normal strength. If it's 20% slower than normal, that predicts it's about 42% of normal strength. So it gives you an estimating approach, even when you haven't correlated as you should, if you're going to use it for accurate prediction of strengths, correlate a non-destructive test result, whether that's rebound hammer, velocity, uh, full out tests, the Windsor probe, other tests you can do. Per ACI 228.1R-19 details these tests, but then you should correlate with tests destructively on cores or cylinders for a given age and condition of the concrete. So that's what you do for a more accurate correlation. But as a relative estimate, we've used it very successfully in a number of projects to get us a pretty good sense of how weak something is. So the relative speeds, I mentioned this earlier, for a Poisson's ratio of 0.2, which is about the same and often similar plus or minus for stone and masonry, as well as concrete. If the P wave speed is taken as 1, then the shear wave is 62% of that velocity, and the Rayleigh wave is 10% slower, or 50%, 6% of the compression wave velocity. So I wanted to give you some basic background in the physics and elastic equations, and now we'll get into the first case history. So this is an interesting project of a historic Grace Episcopal Church in Paducah, Kentucky. It was designed by a famous New York City architect named Henry Condon. He was active in the 1850s and on. He was graduate of Columbia University, and Condon was part of the ecclesiastical movement. So the majority of the churches he designed were stone, but this was in Paducah, Kentucky, more rural for sure at that time than New York City, and it was built of clay brick masonry with lime mortar. They were concerned about the performance of the bell tower in a potential earthquake in that area, as we'll discuss, and they wanted to see that the tower would survive the next earthquake. So there were already signs of distress. We worked with a very good structural engineer on this. He involved us in the project. And the organics and mold and moss were found above the porch roof flashing, as you can see here. There was microspalling above doorways and vertical cracks at the arch doorways as well. Some more of those damages. You can see the avant-garde calibrated crack monitors to show that the cracks were moving, opening, or shifting. Were mounted across many of these cracks in the brick on the outside here. If you looked up at it, there was a break point. So you could see that plus the spall band. So there was obviously aging. And this was done back about, I would say 15, 20 years ago. I'd have to look up the exact date, been just long enough that we did the project. So you can see here some of the cracking that's above the arch doorway. You can see the forces, vertical and horizontal, that are going around that arch. And there's the structural engineer doing some showing how it has kind of kicked out. You can see more calibrated crack monitors. If you're not familiar with these, Avant-Garde sells them. They're normally $25 nowadays. You can mount them with epoxy on each end. You slit a tape, and it has a graticule and a crosshair So we often use them on concrete cracks as well to see if it's opening or closing or if it's stable and it's no longer moving. So you just mount them with that. You can set concrete anchors you want to. Normally, a good waterproof epoxy works fine. So this is the showing that nominally 3/4 of an inch, that this kind of a hinge point, like it kicked out, and the microspalling was up at 16 feet. And we were testing in this zone generally of height from the 0 feet up from the base of the footing. So when I mentioned it's near an earthquake zone, Paducah, Kentucky is about where my mouse is. It's really close to the New Madrid Fault. So they're around 1814, if I'm not mistaken. It may have been 18. Yeah, I think it was 1814. But right in that time frame, it had a massive earthquake that was over, they speculated magnitude 8.4 or greater. And it was felt all the way over in New York City. So it was an enormous earthquake that was very strong and was felt a long ways away. So this is where the church is, and they were concerned that in the next earthquake, it might fail the bell tower. So the bell tower was nominally 2 feet thick. You can see the cracks and spalls, some close-ups of those again in the pictures and the avant-garde gauges again. And the structural engineer wanted to understand the strength and modulus of the existing bell tower, even considering cracking conditions as well as sound brick areas, to come up with an internal retrofit, internal reinforcement scheme to stiffen it so it would survive the next earthquake. Apply a model earthquake, model the whole thing, and design that. But he wanted a better understanding of the material properties than he would have gotten by typical evaluation visually. So as I mentioned, it was to assist in determining the causes of the observed deterioration distress and provide this stiffness data for use in the design of this internally reinforced wall retrofit scheme to survive the next major earthquake. So here we are doing impact echo with an earlier version of our concrete thickness gauge in the upper right, and using surface waves with a computer not shown to take the data, where you have a couple of receivers. They cross. In this case, we're going vertically. You can also go horizontally, but you're sending a surface wave between those two receivers. And in this case, we're looking at the vertical collar joints, or were we seeing debonding at those internal mortar joints, the vertical collar joints, and get it, or did we get a full thickness echo? So we were kind of grading the extent of the damage, both in this direction, and surface waves goes across the cracks as well as gives you velocity versus wavelength, which is depth into the concrete. So the impact echo test is shown here. That small gauge, and we were using a hammer many times because it was thicker. But we have a solenoid built into that with a displacement transducer that'll work out to a foot to 1.5 feet. The walls were approximately 2 foot thick. And so we were often tapping with that small ball peen hammer. There's a close-up of the latest gauge we make as Olson Instruments, our subsidiary company. And it runs into a Windows tablet or notebook and is battery powered and has the solenoid impactor in that. And you can take the data with this simpler, lower cost gauge. We also run it off of some of our more sophisticated recording instruments, but you can do it with your tablet or notebook. So the basic principle is that when you impact it, whoops, I have a very fast, I have to slow that down, I think. I have a very fast scrolling mouse. So this is, when you hit it, you get resonant echoes. It's a resonance test. There's an ASTM standard for it. We were probably the first company, as far as I know, to ever do the test when it was first researched by Cornell University and at NIST also. Dr. Nicholas Carino was funding it and very involved in it. It was research by Mary Sensalone when she was a PhD student at Cornell. And so this, we did the test very early on, I think back as soon as 1986. It was very similar to foundation testing we were doing. So we started doing impact echo a long time back. But the depth, what you amount to is you see these resonant echoes of the time domain, but they're not so clear because really high frequencies get attenuated. So it's better to look at it in a frequency spectrum. So if you do an FFT, the fast Fourier transform gives you the echo resonance. And if that was 6,000 hertz in concrete, then it's 12,000 foot per second factored impact echo velocity. then you would say that's about a 1 foot thick wall. So here you've got the beta factor. It's a shape factor. If there's only a flat slab or wall shape, you get a single echo. And it's because of some physics and the Lamb wave propagation, it's 0.96 of the pure compressional wave velocity is an approximation of that. Depends on Poisson's ratio. But if you have a multiple resonance testing situation, like it's a square beam or column, you get multiple resonances, the factors drop down to 0.82. Sansaloni and Carino did research and gave a table to guide you on how you should adjust your factor to still correctly predict the thickness echo from the back of the slab. So that's the basic idea of impact echo. I put in some velocities for masonry materials because it varies a lot. Ultrasonic, sonic pulse velocities, the compressional wave. And you can see from good brickwork on down the line to poor quality brick, an old masonry with weak mortar, velocities can get a lot slower in the compression wave velocity, going anywhere from 10,000 feet per second on down to 1,200 feet per second in old masonry with really weak mortars, vertical versus horizontal velocities. And obviously, multiple widths of bricks is what's involved in most walls. There'll be more than one width or width of brick, if you will. And then the typical range for concrete, we'll talk a little bit about that, is 12 to 16,000 feet per second. And steel is virtually a constant at 19,000. But deteriorated masonry has a varying velocities because you're looking at this, depends on the number and size of cracks and voids present, the bonding at all these collar joints. So we were grading the impact echo results basically based on it's either a full thickness echo or something shallower from an internal mortar crack in the vertical collar joints, and that would be a higher frequency. So we took this data on a grid to characterize the walls, and this just shows one of the walls where you've got sound results plotted versus multiple cracks versus shallow cracks in the first 6 inches by the diamonds versus the triangles. And they're shown with this symbol kind of like a lightning bolt, but crack widths within 6 to 12 inches. And shallow debonding is also plotted by the square symbols. And the observed crack lines are sketched on this idealized little drawing. So that's just showing the plot of the results, location of the test lines, and things like that. So we had some about multiple cracks. We just couldn't determine the exact depth because you'll get multiple resonances from the cracks. So spectral analysis of surface waves is something that I studied and got my bachelor's and master's in civil engineering, geotechnical, and solid dynamics, structural dynamics, and some geophysics in graduate school at the University of Texas at Austin back in the day, and studied under Professor Kenneth Stokey. And he was my office mate in 1979, started working on surface waves because Ken wanted to determine the variation of velocity versus depth without having to do a downhole or crosshole seismic test, which was boring for seismic design purposes and vibrating machine foundation design purposes. And so he came up with spectral analysis surface waves along with Professor Rosette for modeling. We've used it, and Sohail Nazarian did a lot as a first PhD student and has done a lot still at the University of Texas, El Paso. And basically, we've applied it to pavements and structures as well as the first application. It was kind of the forerunner of what Choon Park at the Kansas Geological Survey did for multi-channel analysis surface waves, which we also do a lot of on the geophysical side of things that we do on projects. So the basic idea is you have two receivers, you impact the material, and you watch how the surface wave, the Rayleigh wave, propagates between them, and you measure that vertical component. And we make this equipment, the ruggedized PC, you can have spacings from 6 centimeters to 80 centimeters. And it detects cracks or flaws that are perpendicular to the wall surface, the depth of them, because it gets faster beyond the tip of the crack. And it gives you general velocity versus depth into the material versus wavelength, which is approximately depth in concrete and masonry. So here we show just a schematic of that with the PC. You're taking advantage of what you probably, well, I always kind of joke with my fellow civil engineers that, do you remember freshman physics? Well, velocity equals frequency times wavelength. They taught it in freshman physics. And so it's also discussed in the ACI 2228 Non-Destructive Testing Committee in this document on non-destructive evaluation methods for properties of concrete that are not strength. And this is being updated currently. But so it's in there. You have a reference to it. It's not yet become an ASTM standard. So this is that basic equipment. You can just see it a little better. We also have a more portable platform. I'm not going to dwell on that, but it's a little more portable. That doesn't do all the processing that a Windows PC can do in the field. And this is example results from a fairly just showing the impact. This is response in velocity units, but basically what every receiver is, and we're using displacement transducers in the testing of the concrete structures and masonry structures. Also, we sometimes use accelerometers. You can use geophones and velocity transducers. But the big spike is that two-thirds of the energy of the surface wave, and it comes after the initial compressional and then shear wave energy. So you window in on that and you mask it out and you get what's called phase. This is what Dr. Stokey figured out with an HP Scientific Digital Signal Analyzer starting about 1979, that it now with digital processing of the data, you can get velocity versus frequency, and that gives you a phase plot. So in a simple sense, when you're this was on a very thick piece of concrete. We were doing a fire damage evaluation of it, and this was the sound area away from the fire. It was a refinery fire that really greatly lowered the velocities to like 3,900 feet per second, so much damage. But in the sound area, you hit it, you process the data, hit it more than once, you can get coherence, and good coherence near one means you have good signals up to about 12,000 hertz. And the wrap phase idea is what Ken applied, that how much out of phase is the response of the receiver closest to the impact with respect to the far receiver's response. So you're looking at this velocity equals frequency times wavelength idea. So this shows, okay, one wavelength, the bar, you can spread out the transducers to 80 centimeters or 2.62 feet. And so that's one wavelength. You literally have a 2.62 foot long wavelength. You take the frequency at that point from this phase plot, where this is 0 to minus 180, this is minus 180 to minus 360. That means it's lagging by one wavelength. The response to the far receiver, simple calculation, velocity equals frequency times wavelength, it's 6,900 feet per second. This is such uniform concrete. This is now two wavelengths, or meaning it's 1.31 feet. You multiply that, you get a very similar velocity. So all of this phase data becomes the dispersion curve plot, where this is plotted as a 6,900 feet per second from wavelengths of 0.8 feet to 5 feet. And what that means on this plot is 5 feet was about this frequency, and 0.8 feet was up in this range. Much shorter, higher frequencies, much shorter wavelengths. So we're getting this velocity versus wavelength, and that'll vary in the materials depending on their properties. If there's damage, if there's cracking, it gets slower. So having said that, you can also do forward modeling, as we did for this project, to make a theoretical velocity versus wavelength dispersion curve to match your experimental data. And then you get shear wave velocity, which can lead you to Young's modulus and shear modulus as well. And that's how we were doing the project. So we were combining all this data. Here is the clay brick masonry on the church going through the wall, starting off fairly slow, close to 1,600 feet per second, and wavelengths of about the first brick, 0.4 feet, up to about the backside at 1.8 feet. And you can see how the velocity is increasing from, say, near 1,600 to about 2,100 feet per second. So when you model it, you can try and match roughly that shape with your theoretical plot in the software. And that just shows how it's pretty close. Again, and what we did to model it is you put in layer thicknesses and velocities. And then it calculates either the corresponding, in this case, P wave velocities were input, and it calculates the corresponding shear wave velocity. You assume Poisson's ratio, 0.25 for the brick in this case, and a unit weight of 125 pounds per cubic foot. These are not the critical parameters because it's really a function of the velocity squared. The shear wave velocity is what's driving the modulus. So that's much more critical in calculating this. And so from this, we then could calculate both shear and Young's modulus, as we've talked about. So how did we calibrate this? We didn't have the advantage of any destructive testing on this project. It was relatively low budget. We had to calibrate it based on visibly sound conditions in openings of the windows and the doors versus really deteriorated conditions. So we could see how the data was in different areas, both in the impact echo and in the spectral analysis of surface waves, so-called SASW method. So that's how we calibrated. It was absolutely critical that we have this basis comparison because we had no other. Basically, we could see where it was really bad and really good, sound versus good. Sound being good, and then bad being the cracked up, deteriorated mortar joints in the old church tower. So we did the comparison testing both across cracks as well as mortar joints that were deteriorated. So we did a lot of tests from different areas and a little too fast again. So I just should stay away from my little scrolling mouse, just too fast. Let's see, we'll go back up. Okay, so the structural engineer was doing this both more senior in his early 50s, getting a PhD at Cornell, and he was doing this to help the church out as well as part of his PhD dissertation. And but a very good structural engineer, very experienced, and he had done a lot of work on masonry, and he applied this discrete pointwise modulus data with a point kriging analysis, and that handles irregularly spaced data. It incorporates anisotropy and underlying trends. We use this software. It's now up to Surfer version 18 or later by Golden Software, which is actually near our office, which is in Wheat Ridge, Colorado, which is quite close to Golden, Colorado, on the west side of Denver. And so he was using this software to take our data. Was aware of Italian research that had shown destructively that from either in-place flatjack testing or prism testing, that Young's modulus was equal to 600 times the masonry strength. And now that is a higher strength, higher strain calculation because that's the working modulus in this case. But he looked at that as a way to quantify our maximum moduli data and predict the in-place strength as well as the in-place modulus. We did measure the in-place modulus, but he was going to approximate it, and he knew the strengths were going to be higher than predicted, but he was getting the stiffness of it. And that was important in his analysis from an earthquake response to get this relative stiffness. And I'm sure ultimately he applied some other factors to that to reduce the strength to something more reasonable. Because nobody really thought that the old brick masonry was 1600 psi. That was about the maximum. And the range he estimated was typically around 500, maybe as low as 300 to 1500 psi. But it was really a stiffness comparison without the destructive correlation. So he had to adjust some numbers, but that was the best way he could get stiffness data from the data we took. So he plotted all these contours. And it was interesting, of course, to note that where there was damage, of course, it was slower and lower modulus. So it was reflecting the damage as well as the basic properties of this. And you can see in these numbers that he's adjusted these numbers down in strength somewhat already from the pure calculation I showed just a minute ago. So these are the contours going around this arched doorway. And here we are looking at it. You can see in this where you've got the cracking damage and the fact that it's slower, a lower strength, I should say. It was a slower velocity, corresponding lower strength, and just showing the conditions physically and comparing the contours that were plotted from the data we took, with both the impact echo and the surface waves factoring into that. So in summary, the impact echo test found the flaws parallel to the wall surface, like shallow delaminations, mortar joints, cracks, and voids. The surface wave test gave the shear wave velocity, which related to the modulus elasticity, and identified cracks and crack depths perpendicular to the testing surface. The NDT results were utilized to give a snapshot, as it says, of the basic structural condition, and it gave a development of a time history degradation of the materials in the structure. So without NDT, structural the engineering would have been based on assumptions and pointwise material characterization, the Kriging statistical analysis, and I like his statement, integrated NDT data into a complete and rational model that moved directly into structural analysis for design of their internal retrofit bracing scheme to mitigate the earthquake risk. So you can see it at gracepaducah.org is the church, beautiful old church. Hopefully it survives the next earthquake, which people speculate when the next earthquake will happen. Some people say 200-year cycle, maybe longer. Who knows? Don't know when the next one will happen. So infrared thermography, shifting gears. We've done moisture penetration studies into brick masonry for wind-driven rain. You can also look for near-surface cracking damage and delaminations in both concrete and masonry. So infrared cameras are out there. You can even get relatively economical ones that do a pretty good job by FLIR that go on an iPhone or an Android phone. If you want zoom and other capabilities with even higher resolution of the changes in surface temperature, you can get a more expensive camera. FLIR is one of the good makers of this. There's a number of manufacturers of infrared cameras out there. So I'm not going to dwell on the equations, but these are the equations. And basically, uh, the wavelength depends on the temperature. With temperature increase, wavelength becomes shorter. And at high enough temperatures, you can see the radiation in the visible spectrum. But this is so-called infrared thermography. Uh, what we're literally looking at when it's delamination, particularly in bridge decks and buildings, if you have debonding of materials, you can see within the first, say, 3 inches or so, as the solar heating, you have to have some heating source. As it warms up in the morning, the thinner piece of concrete or masonry will heat up faster in the morning than a thicker piece because it's more thermal mass. So you see that as a hot spot in your results. And in the evening, it will cool down faster because, again, the thermal mass where the delamination anomaly is will cool down faster because it's thinner. So this shows the wind-driven rain studies. We had helped out the New York City School Construction Authority, which is concerned about wind-driven rains in their brick masonry school buildings. And there's local contractors that have made these spray racks that they just suspend there and literally flood the surface of it, and did it for 3.5 hours. And during that time, one of the easy ways to see what's happening and what gets through the wall is to go inside and take an infrared photograph. And this just shows an example result where the cold water is coming through at a temperature of 28.5 degrees versus the normal temperatures being warmer inside the building. So this was tracking where they were. We could also see the water in this case. The worst case, we could see the water running down the edge of the wall under the north window. But normally it's sensitive. The cold spots show where the water is penetrating. Another picture on a concrete masonry unit block wall. And this is again tested for over a period of time. You can see where the cold spots are. Again, we have moisture coming through in this area. And it's a crack by the change in temperature in the masonry wall, but no water was visible in this case. You can kind of see where it's water has been coming through based on that. Even though the water crack was present, and this showed it up as some cooler things. It wasn't a big dramatic one in this case. So here's a corrosion reinforced concrete building where there's some debonding of the precast panels with architectural concrete colored. And there was, in the placement of it, they ended up with some debonding. And then those are again showing up as hotter spots in this color scale, in this case, back to the traditional approach. So moving on, we're going to talk about some work we did in the 1990s on the Lincoln Memorials and Jefferson Memorials in Washington, D.C. We tested both the concrete, which at that time the National Park Service was maintaining the buildings and fixing some corrosion problems and checking the marble as well. So we did the testing on this non-destructively. And President Lincoln's statue was in great shape. No problem. It's inside the building and covered. But the outside the building and help the tourists, they clean those steps all the time. There's a lot of de-icing salts used that was infiltrating and going down and causing corrosion of the massive concrete substructure that supports the weight of the marble of the Lincoln and Jefferson memorials. And then it's really massive under the Lincoln. This shows some of that concrete substructure. You can see the stairs. You can see the stalactites. Water's coming through cracks. Stalactites are forming from both the de-icing salts and the lime leaching out of the concrete, et cetera, and forming stalactites. So water's coming through. They look kind of pretty, but the real problem is corrosion of the concrete, and particularly the de-icing salts, being close to the Potomac and everything else, it has corrosion problems at that time. And they've addressed them, but this was done a long time ago. But there was visible corrosion in some cases. And when steel corrodes, you can lose up to what you see is going to go at a fairly substantial loss of material. It expands like 2 to 6 times So every hundredth of an inch of corrosion might expand by 200ths to 600ths, which cracks the concrete, spalls it off, and ultimately expose the corroding rebar. To check the amount of steel, you have to shine it up, get to bare steel, and measure it with the calipers to get the remaining cross section. But just some pictures of that corrosion damage. We did the impact echo test as we talked about already, and there's its standard again. We were largely looking for delamination cracking. There we were doing some testing here with an accelerometer at that time before we made those displacement transducers and an instrumented hammer with a 0.2 pound, measures the impact force. We also use that hammer in sonic pulse velocity testing and a small accelerometer to see the echoes. So here we show a result of this echo at about 6,000 hertz, 6.2 hertz. That predicted for the concrete was about 0.9 foot thick. That was basically just 11 inches. And it was a relatively slow velocity, but this was built quite a while back. I want to say it was in the 1920s, 1926 or so when it was first built. So not the strongest concrete. This is another example result, though, where we saw a severely cracked area. It's a higher frequency peak. That's about 11,000 hertz. That is predicting it should have been 17 inches in other areas around it, where we would get a backside echo from that structural slab. And we knew the velocity was, in this case, 12,200 feet per second from tests on cores. And the reflector depth was 6.5 inches. So this was an example of a higher frequency echo that 1 over 6,200 hertz is the echo time, and 1 over 11,200 hertz is the time for that compressional wave to go back and forth. But it's resonantly echoing it multiple times, and that's what we pick up. We also did the testing with the marble. Here we are on the outside, up above, with that instrumented hammer going through it and testing it. And here we saw, interesting enough, the stylobate had multiple echo depths. They were tight. There was still some continuity, but it was showing depths from these peaks at F3, F2, and F1 of 0.9, 1.6, and 2.4 feet. And this is, we don't often do it this way. We don't have to normally, but it's normalized to the force of that hammer. So it's inches per pound force is plotted, and that's how you normally plot it in terms of displacement versus frequency. And you can normalize to the hammer, which does measure the spectrum of the force applied. So we've got good results. We knew there was some cracking damage here. We also did ultrasonic pulse velocity. This has been mentioned, but you can do this straight through, direct transmission. You can do it semi-directly, and you can do it on the surface. But we would do surface waves normally instead of this test because it's a weak signal and it's hard to measure that compressional wave, and you really only get the first inch. So with surface waves, you get the velocity versus further depths, the wavelength, which is approximately depth. So, but you can send it directly through as it shows, and if you had a void, it's a slower signal. You can also do it sonically with an instrumented hammer or 2 accelerometers and a hammer to have an accelerometer here and hit near it. But you can hit it and you measure through thicker concrete, particularly on brick masonry and on marble, using it that way. With ultrasonic pulse velocity and these 50 kilohertz transducers we make, these are waterproof. They can go underwater even, but you won't get much thicker than, say, 5 feet, pushing it maybe 6 or 8 feet. But it's hard to send this weak high frequency signal. When it's that thick, we switch to sonic pulse velocity. So general concrete quality, about 15,000 feet per second. The table explains itself. Good, typical range, 12 to 15,000. The slower it is, the poorer the quality. So here we are doing that pulse velocity testing. This is an example result of both sonic. Here's the ultrasonic result. This had some seamed marble conditions. So there was a very weak signal at 10,000 foot per second at that time. It went around this marble seam, kind of a crack, and showed up as a more rhythmic signal of that ultrasound, the 50 kilohertz signal, at 5,800 feet per second. So this was showing seaming. By comparison, stone can be quite competent. This is a sound result with no seams, and it's showing with sonic pulse velocity, and it was thicker. Here we were testing a column that was 7 feet thick. And so you've got the impulse force of the hammer. That's the time zero. You've got the arrival time, and you calculate 16,600 feet per second. That's a sound, very good quality marble. The marble there is actually Colorado Yule marble from a town called Marble, Colorado in western Colorado that you can still see the leftover columns that did not go to the memorial, but it was a marble quarry that was used for a long time, and they used it for the Lincoln and Jefferson Memorial marble. So we did some Jefferson Memorial testing as well. They were most concerned about those volutes and the top up there at the capitals. Those areas were having cracking damage. In fact, when you look closely, you might have noticed that they have netting to keep the tourists from having pieces of marble fall down on them. So we were testing those to see their competency with a variety of methods. There was also corrosion where they had a lintel shelf where the steel was corroding, causing cracking damage. And there you can see the corrosion in that area. So we did some radar to check for embedded metal. And that was a 1.5 gigahertz antenna of an older GSSI system at that time, pushing it up the wall and taking the data into the unit. And then here you see the vertical leg of the lintel angle, mapping it out. And we found an embedded pin, kind of like a rebar, where this is distance scanned across every 6 inches. And this is time, which can be calibrated to be depth. We also saw the backside of the marble panels over here to the right. So this was a vertical scan result. We also did some scanning down below in some masonry walls, brick masonry that were inside, checking for metal there. We did a cover meter, which can check up to 6 to 7 inches deep. We tend to do a lot more GPR, ground penetrating radar, to find steel because it tells you more. But modern cover meters can estimate the bar size. But if you had bars, obviously not here. They let us drill one single 1-inch diameter core for calibration purposes of our investigation. That's unusual. You normally don't get to touch historic masonry much at all. So with that, we did some borescope work to take a look inside. We really didn't see much of interest. We also did some surface waves work again. We saw on the memorials some weathering, where this was slow velocity on the outside, freeze-thaw damage over time, increasing velocities up to 8,000 feet per second on the surface wave. So it showed about 1/10 of a foot of slow velocity marble. Keep in mind, this is 56% roughly of the compression wave velocity, jumping up to over 9,000 feet per second after 1/10 of a foot deeper. And we saw similar results on this one, 2/10 of a foot of freeze-thaw damage over time. And I will turn it over to Lindsay at this point to let her talk. Go right ahead, Lindsay, and pick it up from here to talk about the rest of it.
All right, sounds good. Um, so I'm going to tell y'all a little bit about some particular projects that I was involved on. So many of you are probably already familiar with ground penetrating radar, and Larry mentioned it a little bit just now, but just quickly going over some of the principles of it. It's particularly useful for locating buried objects, voids, in the case of regular reinforced concrete, rebar. Here's a quick schematic of how it works. On the left, an antenna emits electromagnetic pulses, and the pulses are reflected back off of changes in impedance caused by an object that's different than the surrounding materials. Okay, next slide. Here's a photo of one system on the right here. In this case, it's a GSSI 1600 megahertz antenna with an SIR 3000 data acquisition unit. There's many different kinds of systems with different frequencies that can best suit your needs. Typically, when doing this kind of work, we're using the higher frequency systems that have better resolution at shallow depths. When I say shallow, I mean like 16 to 24 inches. As I mentioned, the antenna emits electromagnetic pulses that propagate through the test materials and reflect back at a change in impedance, which allows us to find the presence of things like embedments and voids. The system records the echoes along with the distance as the system's moved across the surface so you know where you're at. We won't get too far into this for the sake of time, but in order to calculate the depth of the echo, you have to know or assume a dielectric constant, um, which defines the material's electromagnetic velocity. which is then used with the travel time of the echo to calculate the depth of the echo, essentially. And there's the equations that are related to that there. Okay, next. This is what the GPR data typically looks like on the bottom right here. Light and dark show differences in polarity. So in this case, we have two types of features represented in the reflections. You have point reflectors and plane reflectors, which you can see on the top right there. The hyperbola are indicative of single point reflectors, which would be your rebar, dowels, or some other kind of steel embedment that's oriented perpendicularly to the scan direction. Whereas the horizontal line that goes through there is going to be more of a plane type feature, like a void under a slab, or maybe like a gravel layer, or um, a piece of metal even that you're running directly over the length of. And then on the left there, there's just some typical material velocities that are related to those dielectric constants. Okay, on to an actual case study. This was a project where we were scanning concrete masonry blocks of a building to determine if the cells of the CMU blocks were grouted and if there was any reinforcement vertically within or between the blocks. Here we used a GSSI structure scan mini XT unit equipped with a palm antenna attachment, which is super useful for scanning short distances or tight spaces. As you can see there, it's, pretty much palm sized. So we scanned in both horizontal and vertical directions to look for that, the grout, potential of grout in the CMU blocks as well as reinforcement. So here's an example scan across the 8 by 8 by 16 inch CMU blocks. We found that there were actually two types of blocks, both blocks with 2 cells and blocks with 3 cells. So what you see here from left to right is one block with 2 cells, one block with 3 cells, and then another block with 2 cells, all of which are ungrouted, as evidenced by the bright white reflectors there that indicate an air void rather than grout, and no reinforcement in this one. Okay, and another example scan, another horizontal scan. This one has an example of a grouted cell. So you see similarly to the last one, you see these bright white reflectors that are ungrouted cells. And then you have kind of randomly a grouted cell um, that doesn't show a reflector, showing that there's a material in there that has similar qualities to that of the actual concrete block. This one also shows one vertical bar indicated by the green dot there. That's that hyperbolic feature right there. Okay, here is another scan, this time running vertically. Here we have, again, void or partial void conditions behind the blocks in the cells. And you see horizontal reinforcement shown by the dots every 8 inches between each of the blocks. And you can actually see the back wall reflection here too, down at about 8 inches. Okay, so moving on to another study. Excuse me, you'll have to excuse me, I'm getting over strep throat here. Um, so this was a case where we had a marble building and they had these column capitals with these ornately carved volutes at the tops. The volutes had obviously weathered over time and had these leaky joints over the top of them. So they were concerned about internal cracking and damage. We performed sonic pulse velocity tomography at 3 levels around the capitals. Larry already discussed some of the principles of UPV and SPV, but here we did tomography with multiple crossing ray paths in order to generate velocity tomograms to show a more detailed map of slower and faster velocity zones. Larry, could you go back just real quick? The left photo shows the capital with the three levels tested. The top piece, it's kind of a square that kind of curves inwards. And then the upper band and bottom bands where there had previously been steel bands, we tested those circular areas. And then on the right there, you just see the testing in progress. It's kind of hard to see, but you mount an accelerometer at both a receiver and a source point and hit. Okay, next. So the distances between each of those test points were accurately measured using this large set of calipers that you see here. Um, we also had a sound piece of marble available to us from the building that presumably came from the same quarry. And excuse me, that velocity from that sound piece of marble came in around 16,408 feet per second, which then gave us, a calibration kind of to base off our compare the other velocities from the actual volutes to. So the SPV data is processed in a program called GeoTom, which assigns a pixel with a velocity value to each geometric point with a crossing ray path. There's two ways to look at the ray paths and where those intersections would be. As straight rays, which would be the most direct path between the sources and receivers, and as curved rays, which are initially processed as straight rays, then iteratively perturbed until the residuals are minimized. The curved rays are generally used for materials with strong velocity contrasts, and as the marble is natural stone, we tried both of these just to see if there was much of a difference. And we really found that the results were negligible there. So here are schematics showing locations of our 8 test points and the resulting 28 ray paths between all combinations for the round pieces on the left. And then the right shows that top piece, which also had the 8 test points, but you'll remember that the between the points, the square kind of curved in a little bit, so you don't get some of those perimeter paths there. So those have 24 ray paths. And this is a resulting P-wave velocity tomogram from the bottom band with the pixels contoured. Um, each of the 8 test points are labeled there and the ray paths are shown. The green areas indicate areas that are good or sound with velocities that fall within 10% of that sound velocity determined from that big piece. And the warmer the colors get, the worse the velocity is. So the darkest red areas show the places where there are over 50% velocity reduction and the worst cracking, which are between points 2 and 3 and 4 there, and then 5 and 6 with a mostly solid interior. And another example from the upper band velocity, again, with the worst cracking being on the outside perimeter with a mostly solid interior. And then this top piece, which looked pretty bad overall, with the worst parts actually on the inside. You'll remember that leaky joint sat right on top of this piece. Um, and it did look pretty compromised. So this is a table of the final percentages of each tested area that fell within those categories of sound or having a 10 to 20% velocity reduction, 20 to 30% velocity reduction, so on. And as Larry mentioned before, uh, compressive velocity can be correlated to compressive strength, and there's that relative force power relationship between velocity reductions and strength reduction. So although marble is inherently anisotropic, we can make some theoretical correlations to strength reductions based on the velocity reductions in these pieces, which is what we try to calculate here, and that's what is in that rightmost column there. And I will turn this back over to Larry.
Yeah, at the last minute this morning, I decided to put in some testing to give you a little perspective on some semi-destructive testing options. And so I'm going to go through this very quickly so we try and finish close to 10 o'clock. But there are some tests. Obviously, prism testing can be done. That should have said ASTM C1196, I think. I got this typo there. It's in there later. Shear testing, flexure testing, and compression modulus with a flat jack. And the strength of it can also be done with 1197. So having said that, let's just kind of look at this quickly. So you can crush a prism. Obviously, it's not easy to find brick facility owners that want to let you cut out a prism out of a wall, say, and test it in the lab. You can. Very difficult, very expensive. But more typically, prism tests are done by laboratories on new materials. You can, with a flat jack, though, you can get the stress distribution in a building. And the flat jacks were developed in Italy originally for rock mining purposes back in the 1800s. Professors Atkinson and Nolan, who founded Atkinson Nolan. Mike Schuler is still the president today. He was one of their students in Boulder, Colorado, does a lot of this testing and sells flat jack systems. And this is a single flat jack. And basically, they're in Boulder, Colorado. You can have them for a long 2 brick units. You can have them for a circular saw cut or a stitched out square rectangular type saw cut for a single brick. First, you have to set some gauge points because you want to know before you cut anything what the position is between these 2 rows of gauge points. The shelf angle was used for the earlier saw. Nowadays, with a reciprocating saw, you wouldn't have to put in a shelf angle, but you then cut out a slot to insert the flat jack. And that's why the shelf angle is there. The reciprocating saw is much smaller, does a good job. You won't have to do that. You can put a flat jack in there. It's a hydraulic pressurized thing. The simple idea is that you want to jack it back to where the distance between the gauge points was the same point you started from, because that would be the stress in the wall at that point on this outside width of brick. And this shows an example result where you've got over this 20-inch gauge length, 0 psi. It didn't deform much, 200ths, 10,000ths of an inch, 0.02 inches is all it deformed. And then as it's jacked up to 105, 210, and ultimately 280 psi of pressure in the gauge, that is the stress in the wall. And that's restored it to where you started from. It's approximately 0 deformation. If you use 2 flat jacks, which is 1197 versus 1196, then you can get a good idea of the material deformability and strength in situ. And so you put a flat jack on the top, a flat jack on the bottom, have these monitoring points again, and you're trying to compress those materials. And that just shows the removable dial gauge. You could use potentiometers, other things too, but it's getting the distances. So this is a combination of a variety of results for pressure in the gauge versus displacements. The face brick is a higher quality brick normally than the common brick behind it. And you can see it goes up to about 700 psi for a peak strength when it starts to break over. And again, not much deformation, 210 thousandths of an inch. The common brick goes up to about 500 psi. Here's an example result from an old clay brick building in lime mortar in New Orleans. It goes up to about 400 psi. You can see a secant modulus of 130,000 psi, and it rebounded fairly well as it came back down. And it shows the strain levels in this case. So uh, you can also do masonry shear tests. It's important in seismically active areas. They could be done formerly was done by removing a unit. Uh, but with the flat jacks, all you have to do is repoint it. You didn't have to remove things. So you could push it across. There's it, using it with a flat jack. You kind of stitch drill out on each end the materials, push it across. You can see that it left, after the test was done, it cracked the brick above it as you looked at the mortar in the shear strength of these top and bottom joints. When you monitor it with displacement, this came up to about 47 psi at a hundredth of an inch of displacement, and then it just slid in friction. So this was the strength of the shear test result. So I really want to say, both Lindsay and I, thanks to everybody and very much for attending it. Hopefully it's useful to you. We're happy to answer any further questions you might have in the chat or email us. And if you do want PDH, please be sure to email me at larry.olson@olsonengineering.com, or if you send it to Lindsay, that's fine. She is in our Rockville, Maryland branch office near Washington, D.C., and we are on the west side of Denver is our other main corporate office. So thank you very much all for attending. I'll pause and see if anybody wants to verbally ask any questions of Lindsay or I. Be happy to answer them. And I did see, thank you, Mr. Steve Delaroso, for your compliment. I did see, I think Gerard Bolsoff was in there. We've worked with Gerard. He's an excellent photographer in the marriage engineering testing. He attended part of this today. And for those of you who don't know it, he is currently president of the International Concrete Repair Institute out of Minneapolis. So I'm giving him a shout out. I see Gerard is still there. So uh, I wanted to mention that. I also saw Rick Haberberg, who I used to work with years ago at CTL Thompson as a young engineer. So Rick, nice to see you attended. If I know some of the rest of you, I'm sorry I'm not seeing all the names so much. But any questions? So far, we're getting compliments. We appreciate that. And do send us the emails so that you can get it. Like I say, within a few days, we will have it up on there. And I want to thank Lindsay for the excellent job she did. She did very involved in those projects she was showing you. And she's a certified professional geologist, but she's kind of crossed over into the civil engineering world, become a certified bridge inspector, as does a lot of not only geophysics, but a lot of non-destructive evaluation projects for us in our office there, along with Wade Martin, who's a senior project geophysicist back there and also does a lot of non-destructive evaluation. So we're not every place, but we're happy to help you out on your projects. If you're interested in instrumentations, by all means, uh, we'd be happy to give a local one to your local group or some other things. Okay. So I don't see any questions coming through. That either means we did a great job. I see Pablo Del Monte, know him as well. Excellent. And Lindsay, I don't know if you recognized any names or not of people you wanted to shout out, but we'd like to get to know the rest of you. And if you're ever in Denver, come see us. If you're ever in Rockville, reach out to Lindsay. They don't, because it's the DC traffic, what it is, they're not always in the office. So just don't go by the office without checking with us. So I see Neeraj took it. Excellent. Any other questions before we kind of close it out? Okay. Okay. Well, we came pretty close to quitting on time. It's 10:03 a.m. So if we don't have any other questions, we'll go ahead and close it out and say thanks again for all that attended today.